Hello and welcome to this video out of my Networking Basics series. I'm Wolfgang Tremmel and I run the DE-CIX Academy. So, if you're interested in more videos, just head over to the DE-CIX website, decix.net/academy. There you can find more content like videos, downloadable papers, and so on. But now let's get started with networking basics. And today I'm talking about TCP, and that's the Transmission Control Protocol. If you have a look at the other webinars I did in the Networking Basics series, I started with networks in general, talked about Ethernet, talked about IP and routing, and in the number 4a, I talked about UDP. Today, talking about TCP Transmission Control Protocol. If you remember, the internet model is built out of layers. And on the IP layer, that's layer 3, data units are called packets. And here we have the IP addresses, and the IP layer is responsible for end-to-end transport. Above the IP layer, we have the transport layer. And the transport layer, it may provide flow control, reliability, congestion, and congestion avoidance. Also, it may contain information about the next layer up. Examples for protocol on the transport layer are UDP, which has none of these features, and TCP, which has all of these features. I talked about UDP in the last video. I'm talking about TCP today. So, TCP, Transmission Control Protocol, what does it do? Well, very simple. It transports data, any kind of data, like emails, like your web page, like pictures, like encrypted files. Any kind of data can be transported by TCP. And TCP makes sure that your data arrives at the destination reliable and unchanged. And it lets the sender know that the data has arrived. It takes also care about the speed of the delivery so that the sender doesn't send faster than the receiver can receive the data. With all these features, yes, TCP is complicated. And how to do that in a short video? Well, one option would be to oversimplify. I'm not doing that, or leaving stuff out. And yes, there is many more to TCP than I'm talking about today. I'm talking about the basics features of TCP today. If you want to read more about it, at the end of the downloadable slides, there is a number of pointers where you can go on reading. So, transporting data, how does TCP do that? Well, it establishes connections, and not one connection just from the sender to the receiver, but actually two connections, one from the sender to the receiver and another connection back from the receiver to the sender. So on a TCP connection, data always flows two ways in both directions. Also, each data received is acknowledged, so the sender knows what the other side has already received. And if anything gets lost, think about packet loss, you've all heard that term, then it is retransmitted. But if anything has to be retransmitted, keep in mind that costs time. So, encapsulation, packets inside packets, headers after headers. Encapsulation is like the Russian dolls. Ethernet frames have an IP payload. IP packets have a payload. And this packet inside IP packets usually is either UDP or TCP. and there are others as well. But today, like I said, we're talking about TCP. So we have a TCP packet inside an IP packet. Let's have a look again at the IP header. We have the IP version 4 header, and in that IP version 4 header, we have a protocol field. And this protocol field tells what kind of payload follows. And in terms of TCP, the number 6, well, the number 6 in the protocol field tells that this TCP header follows. In IPv6, we have quite the same. Just the field is called next header. It has the same values. So here again, also number 6 tells a TCP header follows. So what's about the other fields? We talked already about UDP. TCP is way more complex. So also the TCP header is more complicated. Let's have a look at the TCP header. So here we have it. A bit more fields than an UDP header. So we have the source port and destination port. That's quite the same like UDP. It's each 32 bits and both are mandatory. So both are required to be filled out. In UDP, only the destination port was mandatory. We have a sequence number, and this sequence number is a pointer and it starts at a random number. We have an acknowledgement number. How acknowledgement number and sequence number play together, I'm explaining in the next slides. And the acknowledgement number tells the sender what is expected next. We have a field called window size, and that's the amount of data the sender can send to the receiver without acknowledgement. We have a checksum. The checksum covers parts of the IP header and the TCP header and the payload. The urgent pointer, well, it marks the payload as urgent, but that it's not widely used. I have no idea if it's still used at all. It was used to tell the application, the next layer up, that the content is urgent. And of course, we have flags and options. So there are 9 flags in the TCP header. And I'm covering the most important one. So there is the so-called syn flags. That means synchronize the sequence numbers, and that's basically what starts a TCP connection. The flag is only set at the beginning, at the start, when the connection is being set up. Then we have the ACK flag, and that means that the content of the acknowledgement number is valid, and that should be set in all packets after the initial handshake. We have a push flag, and that means for the receiver, push all buffered data up to the application layer. The fin flag tells that this is the last packet from the sender, and it means the sender is closing the connection. And at last, I'm talking about the reset flag. That means shut down the connection immediately. Something is wrong. Yeah, features of TCP. Some of them are the same like UDP. So we do have port numbers. If you did not watch the UDP video, shortly explained what are port numbers. Just imagine we don't have a computer system, we have a building. And I want to deliver a letter to one apartment in that building. So I'm addressing, that's the IP address, the packet to the building, and I add a port number. And this port number basically tells to which apartment this letter has to be delivered. In reality, of course, we do not have an apartment, we have a computer system. And also we don't have apartments or letterboxes in that systems. We have programs, we have software running and listening for incoming data. But we do have port numbers, and behind each of these port numbers sits a piece of software, and if the port number in the packet matches that port number of the system, the data is delivered to this piece of software. On some systems, this kind of software is called a daemon. So that's about port numbers, and it's quite the same as in UDP. Talking about connections, setting up a connection in TCP. And for that, we are doing a so-called handshake. How does that work? Well, it says, hey, I want to connect to you. And the receiver answers, oh, that's fine. I also want to connect to you. And the initial sender also says, all right, that's fine. So this is why it's called a three-way handshake. We have three stages: setting up the connection, acknowledging the connection, and setting up the connection backwards, and acknowledging the connection backwards. That's the three-way handshake. In reality, with packet, it looks like this. The sender is sending a TCP packet with the SYN flag set. The receiver sends back another packet also with the SYN flag set and with the acknowledge flag set. And the sender, you might have guessed it, just sends a packet back with the acknowledgement flag set. And that's the TCP three-way handshake. And this is one of the criticisms of TCP. Some people say it just takes too long to set up a connection. Think about latency, think about how far away sender and receiver can be, and before data flows, 3 packets have to cross the ocean. Next feature of TCP is reliability. And that means, has the data arrived, and also let the sender know about it. So I'm sending a packet from Europe to Australia, and the receiver sends back an acknowledgement. And it's doing that not nearly for every packet, but every now and then, so the sender knows the data has arrived. That's called reliable data transfer. Every now and then. So I don't have to do that for every packet. There is no need to wait before sending the next data. So I'm not sending a packet, wait for the acknowledgement, and then send the next one. The sender constantly sends packets, and the receiver constantly sends acknowledgements. And this is to time also the delivery. So let's go back a slide. Let's have a look again. The sender is sending the packets, the data, and the receiver is sending back acknowledgements, and the interval of the sending packets is the same like the received acknowledgements. And the sender now knows the data has arrived. This is what we called ordered transfer. So everything is fine if the packets arrive in the same order like they have been sent. But the network, well, it's possible that one packet gets delayed and is delivered late. So this is what we called out of order packets. So how does the receiver know which packets belongs where? And that's what the sequence number is for. The sequence numbers takes care that the receiver knows where to sort in the received data. And retransmission of lost packets, that's what the acknowledgement number is for. So let me show you. So the initial sequence number is random. That's for security reasons, so an attacker can guess the right sequence number. And the initial sequence number notes the byte number of the first payload bytes. The acknowledgements are sent by the receiver, and that means I have received data up to this sequence number. So acknowledgement number and sequence number are tied together. Sequence number, the number of the byte. Acknowledgement number, I have received to that byte. And if anything is missing, the receiver simply doesn't increase the acknowledgement number. So if a middle part is missing, the receiver sends over and over again the same acknowledgement number, so the sender knows, hey, the receiver has received everything up to here and there is something missing. Let me show you with a diagram here. So sequence number, I'm starting with 1 to make things easy. I'm sending 10 bytes of data, and I'm sending the next sequence number 11. So I have sent 20 bytes of data. 10 bytes plus 20 bytes is 30. So the receiver sends back, I have received 30 bytes of data. And now the sender knows, okay, everything is fine, I'm sending the next packet. Of course, in reality, he just wouldn't wait, he would send it, and by receiving the acknowledgement packets, he knows what has arrived. And the next packet, okay, he sends 10 bytes, so 40 bytes were received. Now, how do we deal with packet loss? I'm sending 10 bytes of data, like before. I'm sending 20 bytes of data, and that gets lost. So the receiver sends back, I have received 10 bytes of data. The sender now knows, oh, there was something lost, and he sends back the next packet, and he still gets the acknowledgement number of 10. And that means he has to retransmit the packet. So this is how we're dealing with packet loss. The next feature is flow control. And this is about how fast senders can deal with slow receivers. Flow control is about end-to-end communication. It's not about the network in between. And the idea is that the sender should not overload the receiver. And this is what the window size field in the TCP header is for. And the definition of window size is the amount of data the sender can send without an acknowledge of the receiver. So what happens if the receiver gets overloaded? Well, it simply reduces the window size. And that means the sender has to wait a little bit longer and before sending you data until he gets an acknowledgement. So if the sender has sent the amount window size data, it stops until it receives an acknowledgement from the receiver. This is how the receiver can control the sending rate of the sender. Yeah, when everything like that was designed, networks were way, way slower. So the original window size field was 64 kilobyte. And this is very much too small for today's terabit extremely fast networks. So there was a window scale option introduced, and that means multiply the window size with 2 times n. And usually on Linux that's 1, but you can be bigger. So that means you can have really, really big window sizes. So for really fast receivers, it's possible that they say, send me a lot and I'm acknowledging slower. Last feature of TCP, and that's congestion control. While flow control was about the end-to-end communication, congestion control is about dealing with the bottleneck between sender and receiver. And the idea is, do not send more than the network in between sender and receiver can transfer. TCP uses a sophisticated number of algorithms for that, and they are called slow start, congestion avoidance, fast retransmit, and fast recovery. And again, it's getting complicated. So slow start, what's that used for? Well, neither sender nor receiver do not know anything about the network in between. Can be a fast fiber network, can be a slow satellite connection, can be anything. And these two algorithms, they limit the sender. And the sender keeps track, they keeps a variable for each of their connection. And first variable is called congestion window. And that's the limit of data that can be sent before receiving an ACK. Do not mix that up with the window size. So the slower of them basically applies congestion window, window size, which each of them is slower, controls how much data the sender can send. And the next variable is called slow start threshold, and that means I'm switching the sending method from slow start to congestion avoidance. And slow start means I'm starting my sending algorithm, well, slow. And slow start is always used at the beginning of a connection or after packet loss. So if packet loss occurs, the sending method falls back to slow start. At the beginning of a connection, the initial value of that congestion window variable is set depending on the maximum packet size of the sender. And usually it's 2 to 4 packets. And once an acknowledge is received, the congestion window is increased and increased and increased. Each acknowledge increases the congestion window. And once it's big enough, so bigger than the slow start threshold, the algorithm congestion avoidance takes over. And the idea is not send more than the network can transfer. And basically what you're doing, you're pacing the sending rate to the acknowledgement arrival rate. This is why latency is so important. The lower the latency, the faster the sender is sending data. We are increasing the congestion window for each of these round trip time. And like I said, this is the reason low latency is important. And that continues until there is a congestion detected. So, congestion detection. Well, what happens? When a sender receives an out of order packet, it sends a duplicate acknowledge immediately. So the sender knows something might have been lost or reordered. If 3 of these duplicate acknowledge comes back to the sender, the fast retransmit algorithm kicks in. That means the sender is resending missing data immediately without waiting for a timer outage, and after that another algorithm takes over, and that's called fast recovery. Like I said, TCP is complicated. If you do not understand how all fits together, I really suggest that you read up. There is some material, some pointers at the end. So fast recovery means getting back on track, getting back to congestion avoidance. And that means after resending, new data is being sent again at slower speed, and that happens until the acknowledgements are received normally by the sender. And then we start all over again using the congestion avoidance algorithm. So, question: is that everything about TCP? Of course not. TCP has many, many more extensions, and I'm not talking about them today. Have a look at the material, download the slides, and read the RFCs. So, what's TCP used for? Well, the list TCP used for is way too long. Most applications today use TCP, HTTP for web browsing, SMTP for transporting email, SSH for secure login to remote systems, and many, many more. Conclusion. What did I talk about today? I talked about TCP, the Transmission Control Protocol. TCP is a connection-oriented protocol on the transport layer. Connection-oriented means we are setting up a connection, transporting data, and then shutting down the connection. TCP uses sophisticated algorithms for reliable data transport. Remember, everything being sent is received and the sender knows about that. And for that it uses an end-to-end acknowledgement. TCP tries to be efficient in the use of available bandwidth. And it does that by increasing the sending rate step by step until a congestion occurs. TCP also, and I did not talk about that a lot during the presentation, tries to be fair to other connections. And it does that by not overcrowding other TCP connections. And that's it. Thank you very much. Thanks for listening, and please download the slides, read on about TCP. A lot of things have been added over the years, and a lot of things have been changed, mainly because networks got faster and faster, and TCP needed to be adjusted to that. Thanks for listening. See you next time. I'm Wolfgang Tremmel from the DE-CIX Academy. Bye-bye.